Okay, so here is our actual lesson 1, and if you remember from last session, what we want to do initially, we start to talk a little bit about a few of definitions. You are not responsible for memorizing of any of the definitions because you always can find them in Wikipedia or you can Google them, so there is no point to memorize. However, you have to have an understanding of this type of terminologies because we will use them quite a lot through the course. And one of the first things that we want to define is the definition of image and the definition of digital image. And the reason we want to define them because this course is called digital image processing. So, what is an image? In general, I mean, you don't need to look at the definition from Wikipedia, which is there. What is an image?
Picture.
A picture. And mathematically speaking, it's actually a function. It's a function of f of x and y, which means that you can go to any rows and any columns and read what a specific value, right? Now, in general, the picture that is being created in back of our retina, our eye, what is it, a digital image or an analog image? An analog image. You all are in the world, are you digital or analog? Analog. Everything in the world is analog, right? What does it mean it's analog? Strong. What you said is correct. What you said is also correct. But I want a stronger definition. When we say analog in English literature, what does it mean?
There's physical properties.
Well, what does it mean? It's a physical property. That's correct. But what does it mean?
Non-distributable. It means the time frame is not distributable. Not perceived by.
Your definition is stronger, but it's not like that. All of you know it. It means it's continuous, huh? Continuous function is analog. But what do I mean continuous? Is this discrete? Is this an analog signal? So this is RA. Time, and this is FT. This is open. This is closed. And it continues, right? It starts from minus infinity, blah, 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 comes, and then goes. Is this an analog signal?
Yes. No.
No. Yes.
There's information missing, so it's not continuous.
Now, when we say that something is analog, and we say that it's a continuous function, it continues over the time. In other words, for every range of time, you have a definition of your function available. So magnitude-wise, you can have different values. We don't care much about that one, but over the time, it is continuous, so it is analog. So in other words, a function like f, x, and y is an analog image because the value of x and y can be any number. In other words, between 0 and 1, you have infinity many placements that you can put, right? And then, what about digital image?
Well, if the 0 and 1 it's fine.
You define binary. 0 and 1 means binary. We are talking about the term digital. So what does it mean if something is digital?
It has finite amount of values.
It has finite locations. It has finite locations. So the function f, x, and y, you cannot have any value for x and y. It's a finite places that you can go. So it's discrete. What else? When we say that something is digital, it means two terms have become discrete. One is that you cannot have value at any place, right? It's either you have a value here and then there in between you don't have anything. Between numbers 0 and 1 you don't have infinity placements. Another thing is that although you have limited places, the value that you can assign cannot be anything. It's also quantized, right? If you remember 2 days ago when I was giving a very, very basic introduction, we said that all the images that we have are A-B, which means that it can be between 0 to 255. You cannot be above 255, you cannot be below 0, right? So if your magnitude is also quantized and you can have some specific value, and your location are sampled in a way that you have some fixed values or discrete values, then we say that that function is a digital function, or in other words, that image is a digital image. In other words, what happens is that they are digital if the amplitude is finite. We have value between 0 to 255. We cannot have any number, infinity many numbers. And also the location which we are putting the pixels are all discrete. They are all discrete. So we have two things. One talks about the magnitude, the other one talks about the locations. And these two, the locations, is usually referred to the spatial properties of an image, and the value that we are assigning, this final value, is referred to intensity of an image. So the spatial and intensity are the things that we are talking about the digital image. Now, in the whole course from now on, when I use the word image, I mean digital image. Okay? I mean digital image. So I don't use the word digital image anymore. So when I say image, I mean digital image. We don't deal with anything which is analog and so on. How old is the first digital image? Do you know? The first digital image is almost 100 years old, which in 1920s it was being produced. One of the first application of this digital image, you can see it. And it was used for the news reporting. Yeah?
Sir, I'm asking a question. We are talking about digital image. Is there any concept of analog image as well?
Well, we see each other, right? So there are lots of concepts of analog image because we are all analog. But why do we talk about digital image? Because in analog image is what our eyes get. We have practically infinity many information. So why do we go for the digital image?
Because we want to process it, right? We have to make the image digital first for us to process it.
No, if you want to, if this is here on my palm and you want to pick it up, you look at it, right? You walk towards it and you will take it. So your brain does everything in analog form.
So it's
The
our brain.
computer,
Yeah,
the computer is what we are using to do the processing, and it is a digital environment. So we are forced to have the image to be digitalized because you put it into the computer. So you have to feed it as zeros and ones. That's why that we are talking about the digital images. Okay. So this was the first application of the digital image, and the first ever digital image which has been produced by scanning happened in 1957, so around half a century ago. And it was a picture of this guy, Russell Critch. He had a baby and he scanned the picture of his baby. So it was the first ever reported scanned digital image. Anyway, forget about the history and coming back to our Obelix picture, let's see that what are the foundation of the digital image that we have. Typically, if you have an image, because we said it's a digital image, it means that you have finite places, you have places, discrete places, which you are putting values. Now, these discrete places are called pixels. Discrete places are called pixels. So it's like that I have an image and I have lots of locations, right? And these are the unit location. In other words, you cannot divide them into the smaller place. Each of them is called a pixel. So it is discrete because I cannot have anything between this location and the other location. If it was continuous between the point 0 and point 1, you can have infinity many points. But if it is integer and discrete between 0 and 1, you have nothing, right? And then, apart from that, because it is digital, in other words, if the value is quantized, what I can write inside here are limited between 0 and 255. Because all the images that in this course we discussed are on-site integer 8-bit. With 8-bit, if you remember, I draw this. With 8 location, the maximum number which we can show is an on-site integer which has all these 8 locations to be 1. which makes it to be 2 to the power 8 minus 1, which is 255. And the smallest one, of course, is everything to be 0, which is 0. So every single place that we see can have a value between 0 and 255. And this small part, which is the fundamental part, or building block of an image, is called a pixel. And typically, when you are talking about the resolutions of the image, you usually say that, okay, what is how many pixels do you have inside your image? And they said that, yeah, I have 1200 by 1040. So you are talking about the number of rows and columns that you have inside your image, right? So this talks about the resolution. So as I said, when I use the word image, I mean a digital image, and I mean an image which is a grayscale image like what you see, and it has 8-bit representation. So every single pixel, as you can see here, this is 1 pixel, it has a value between 0 to 255. 0 means black, and 255 means full value, which is white, right? So here is another example. I am taking a portion of the rock of the Obelix, and if I look at it, it's like it's a matrix of the numbers, and these are the values that I have. These are the values that I have. So from computer perspective, an image is just a matrix of numbers. And here you can see that the first location has the value 103, the last location has the value of 88, so you can click on any places in order to see what are the values that we have. Now, because in the digital world, we are having limited places and limited values, it means that in the real world that I see everything in the analog form, when it comes to the computer, it will become kind of an approximation because I'm picking this place and that place, and what is in between will be gone forever, right? So, but however, we are having very good resolutions camera, very good resolution acquisition devices, so the number of samples that we are picking up are so much that we cannot understand that it has been digitized, right? It has been digitized. With a microscope, you are taking a picture which is like very, very high quality. You can zoom quite a lot into it, and you will understand that it has been actually sampled. But the reality is that when we digitize anything, it will become an approximation of that. However, the error is usually so small that you can neglect it. Yes?
So, but this is for a scalar image. But then why, let's say, we use a vector-based software, then we don't see pixels, right?
Well, I mean, there is one thing is, you have a matrix. You don't have an image. You have a matrix and a number. That it happened when you do the visualization of this matrix, you see Obelix. Now, this matrix is made of lots of rows and columns, right? So what happens, typically, we take this number of rows and we put them next to one another. So you have a vector that you see. From computer perspective, you are just replacing your numbers. And you know how you replace them. You can reshape it back into here and visualize it, and it sees the Obelix. So when I show the picture of Obelix, or I show the picture of the Lena to my computer, it doesn't react because it doesn't care. It's just a matrix of the numbers, right? So it's a matter of how you are representing based on your application, but still, this is a discrete, a digitized matrix. This is a digitized matrix because it is not an analog. It cannot be inside the computer. Our voice is analog. Our ears here analog. But what happens is that when you talk to the microphone, it automatically passes through something which is called analog to digital converter, and then it will be processed in there. And when you are playing it through your speakers, you see that there is a DAC, digital to analog converter, and convert it to the analog so you can be able to hear it. Right? Did we answer your question, or your question is completely different?
Yeah.
Okay.
My question was, if we take Photoshop,
Okay.
if we zoom it in, then it will
Yeah.
get pixelated. But with Illustrator, it's a vector-based, and we zoom further in NVIDIA. That's I'm asking.
No. I get your point, and I now answer that one. This is something I studied also. Now, what happens is that you see a very nice picture of Obelix, and then you start to scroll and zoom and zoom and zoom and zoom in Photoshop, as I said. And then what happens, at some point you start to see this blocking effect, which means that you will be able to see the fundamental parts of an image, which means a pixel. However, a pixel is one value, but here you can see that you have maybe a series of values. So what happens, because of the visualization, it does some interpolation in the background. In other words, it might start to repeat some of the values. So when you are trying to visualize it, you're asking a question. When you are visualizing your software applies some other algorithms at its back, but it doesn't mean, or it doesn't contradict the fact that you have a discrete value in your hand. Easy thing is that if you're using MATLAB or OpenCV, just read an image and see the matrix that you have read, and then you will see that it's all discrete values that you have in front of yourself. So we do lots of approximations. Okay, I want to do this. One of the very most frequently used aspects in image processing and in computer vision is a term which is called psychovisual effects. You know psychology, right? Because when we are talking about image processing, our baseline is, what is the baseline in image processing? Sorry?
What do you mean by baseline?
The baseline, like how do you compare all your things with?
The white. What you see.
You are right, with human, right? Our baseline is human. The whole thing is to try to mimic the human. So we are always saying, try to see that how better or worse we are from the human, right? Although you always compare between the different methods, but the whole aspect is that whether we can behave better than human. So it's very important when we are developing something, consider human being. That's why that this psychovisual effect will become very, very, very important, right? Very, very important. How many tones of colors do we have? Like, for example, how many tones of reds or greens do we have?
Infinite number.
Well, I mean, we have theoretically infinite numbers. I read once an article in the Nature that exists over tens of millions of tones of green. I mean, if you ask, maybe 3 or 4 greens are available. If you ask some of you who might be an artist, maybe you say 10, 15, or 20 of them are distinguishable. The other ones, theoretically or mathematically exist, but we as a human, we cannot see it. Right? We cannot see it. Let's say that you take a very nice photo of you from a very nice place. Let's say you go to Viljandi and took a very nice picture of the Viljandi castle with you do a selfie, and you send it to your parents. And they say that, oh, what a nice picture, what a nice view, you look very handsome, you look very pretty, and so on. And nobody comments about the details of the hair, because the details of the hair doesn't exist in the image. Due to the compression, we kill them. But nobody realizes it, because we don't realize it. Our eye cannot detect it. So it means that sometimes there are some details which are actually very expensive to keep them. You can keep them out without anybody noticing it. Right? Without anybody noticing it. And it is like, as a Jewish man, let me give you an example of money. You have 1 million euro, right? And your friend's kid come and he takes 50 cents from your money. Would you realize?
If I
As
have
a Jewish man, I do realize, but I mean, in general, you don't. Why? Because your baseline is a matter of millions, so you are taking a 50 cents out, right? So this is the whole thing. Sometimes the details are so small when you compare with other things, which removing them, you wouldn't realize. Imagine the same example of taking the photo and the details of hair are not important, that I zoom in to his hair and take a picture of his hair. Now, if I remove some of the details of the hair, this will be very visible, right? So psychological effect says that to the approximation, human won't understand anyway. So especially when we talk about the compression towards the end of the semester, you see it's a very important factor. This is how JPEG works, right? This is how JPEG works. We look at these psychovisual effects, and we benefit from them. We benefit quite a lot from them. Yeah.
I have a question about what does height mean in these pixel values? Like represent gray levels, colors, and heights.
By height, I meant the size of the image.
Oh, okay.
Yeah.
Okay.
We will get back to these words a few slides later when we talk about the resolutions. This is one of the new things that we will learn today. So, now that we know what is an image, you know what's a digital image, so let's see what is a digital image processing. And I asked you 2 days ago, what is a digital image processing? And some of you answered that it is processing of a digital image, which is the definition of digital image processing. And then we gave an example of a digital image processing, right? And I remember one person shared the same experience with me, that Microsoft Paint is one of the coolest or simplest tools that we use to do this digital image processing. And I asked the examples. Can you give me now an example of an image processing that you have done in your life? One example. Cropping, right? You take a picture and then there is somebody in the scene and you don't want it, or some part because of the lighting is not good, you just crop it before you put it into your Facebook. This is a very simple task and it can be inside image processing. What else? Is there anybody who works in a company and somehow you are using image processing somewhere? Is there anybody? Yeah? Yeah. What do you do?
I'm writing a mobile app that processes video in real time and text.
So what does it do?
It's looking for light sources, essentially.
Light source. Looking in the light source, like our high intensity values in a frame or in an image, is also a processing of an image. Why? Because you are starting to compare some pixel values. You start to touch your pixel and do something out of it, right? And here, in this course, we will talk about a few of them which are very important. And I have this picture of Obelix, and we go over all of the things that you will learn in this course. But it doesn't mean that the processing of image is limited to these tasks. As I said, it can be as simple as cropping or as complicated as many of the filters that you have in Instagram or Photoshop, right? Now, the first thing is conversion of the color image into a grayscale image. Turning from color to grayscale is processing of an image. Converting of a grayscale image to color image is also processing of an image. Now, the question is that if I have this color image and I convert it to this grayscale image, and I use this grayscale image and I color this one, do I get the same image?
No. You can, but you have to select it and then.
Do I get the same image?
No.
Is it
Yes
yes or
and
no?
no.
It's just like, do you love me? Yes, but. So, without any constraint, is it a yes or no?
No.
Yes, it depends. If it's a raw image, you can get that.
The answer is no. And you can prove it by math. Proof it by math means that very solid state. And the simple thing is that here we have 3 layers, and when we come to grayscale, we kick from 3 layers to 1 layer. I cannot say that we kick 2 of them out. We actually kick all the 3 out and somehow we extract 1. So from 3 value, you get to 1 value. Do you know what type of function it is? It's called an onto function. If you want to have a function to be reversible, it's a mathematic. If you don't know it, that's all okay. If you want to have a function, you're a PhD student, huh? So if you have a function and you want to find if a function is reversible, what should it be?
It should be undoable.
No, it should be 1-to-1.
Yeah, 1-to-1. Okay.
It must be 1-to-1. If it is onto, can we find the inverse of it? No. Right? What we can find is a pseudo-inverse. That's why that if you have this and you convert it to the color, you say that, oh, you do the pseudo-coloring. Do I get exact color? You may. You might be lucky. It might be a chessboard and you get 100%, right? But you don't know, it's always an approximation. There are lots of software that you can use to do it, and typically, it's a real life example. There was a very old, I have never seen my grandparents, right? So they were all dead. My mom had a very old picture of her dad, a black and white picture of her dad. And then there was this, that I was a kid, very popular to colorize the pictures. So she took it to this Photoshop and then said that, yeah, this is the old picture of my dad and I want it to be colorized. And I remember the guy asked, what was the color of your dad's hair? What was the color of his eye? So these are the real information that you provide. Because if the color of the eye is green or blue, they have the same representation in the gray tone anyway. So you cannot go back. You cannot go back unless you say that this is that specific thing. There are also very famous British comedian. You might be too young to know them, called Laurel and Hardy. One of them was a very fat and the other one is thin. Okay, they are American, the thin was British. And their movie, one of their movie called The Piano, is the first movie in the world which has been converted from gray 11 into color one. And lots of people, I remember it was on BBC, that hated it because the person who painted it or the algorithm that colorized it, they did it wrongly. The Laurel one apparently was a redhead person with a, I don't remember, blue eye, and they colorized it in different color, right? So in other words, it's a one-way process. It's a one-way process. You can approximate this one back, but you don't get it necessarily. Yes?
But this is like if we have a JPEG or a TIFF, and if we unsaturate it, and then if we want to colorize it again, then that happens. But for instance, I have taken black and white pictures with RAW format. And then if you put them in Picasso, for some reason they colorize.
Yeah.
What's that?
It's got magic, right? So. And it gets to this. I mean, I paid him to ask this question so I can answer this. It sounds cool on YouTube. The thing is, nowadays, we are living in the area of 5G, right? Your flash memory is like, I don't know, 100 gigabytes. So you don't have a space problem for one single image. So what happens, you have an image, and next to it you have a table which is called metadata. As a student, we call it a cheat paper in your pocket. So, what it is, I tell you, what's your name?
Arvind.
Arvind.
Aru.
Aru. It's cooler. Aru, you have number 1 at the top, you have a number 1 in the middle, and you have a number 1 in the bottom. Right? And all of them goes to number 0. And I tell you this, I have number 0. Can you tell me that what is the input? Is it 1 up, 1 middle, or 1 bottom? I have 1 top,
Okay.
1 middle, 1 at the bottom.
Okay.
And all of them goes to 0.
Okay.
And I tell you that I am 0. Can you tell me that what is my source?
What is the source? Is it an AND function? What kind of functions do I have to check?
I am 0. Can you tell me that what is the function? What is the input? Which one of them was my origin? You can't.
Yeah.
You can guess. However, I said that I'm 0. Can you tell me that where is my origin? I am in the middle.
I'm in the middle, then you say
Then
that's
you
the
say
middle.
this. I'm in the middle is the meta file.
Okay.
So, in order for having that, then you have to sacrifice more space. You have to provide it. Right? So in other words, you don't do the quantization. You keep them. Right? The whole aim of quantization is that you kill them. And by killing them, it means that you cannot get it back. So this is a very important concept that you have to keep it. If you are using MATLAB, you will see that in MATLAB, if you downsize, if you sample this pen, you will get a smaller pen. And if you interpolate, which is an approximation technique, you get the exact thing. So you have a student start to have conflict. Then what happens? Because it was keeping all the things in its back. It knew that where the things are coming from. Right? So in the reality, when you downsize, it will be gone. Why? Because your Hubble telescope downsize it, and it is gone forever, and it send it to you. So you never have it. However, we are in era of 5G, right? You are in era of 5G, so you don't have it. You're a student. You don't have enough money, so you don't have very strong, let's say, TV sets at home. So you watch everything in HD. I pay more. They deliver me the meta file, and I watch the same thing in 4K. So, but this is the reality. That's why that for 4K you pay more. You actually pay for the meta file that is being sent over the IP to you. And this is also another hot topic, which many people like Huawei in China spends actually a huge amount of money on that. And it's called interactive multi-view selection, right? Interactive multi-view selection using that. Again, it goes too far from our nice digital image processing topic. Yes, sir.
So building upon this question, then I've seen like videos where like you have NASA's telescope picture, and then they first zoom it, and then it's like a blurry image, and then all of a sudden you see the Milky Way. What's that then?
Okay. You go in the tunnel when you are driving, and you watch your YouTube video, and then your YouTube video still plays, but the quality drops to very bad. You can see lots of blocking effect, but the video continues, and you get out, and it gets back to the very high resolution. So this is actually what Huawei was doing. You define some very low level which you transmit, and you can always transmit it. And then if the bandwidth permits you to transmit more of the metadata, so it will become more accurate, more accurate, more accurate, more accurate, more accurate. I mean, whatever you say is not contradicting at all with this. You are absolutely okay. Do you want to turn back towards the classroom, my Chinese friend? Or do you want to turn back towards us? We like to do.
I now understand what you are discussing right now.
Yeah. I know this stuff, but we will get to that in a moment. So this is a grade. This is a grade level, and getting from here to here, we are losing lots of information. And we can get back by doing the approximation, and all of this is an example of image processing. Why I talk about this? Because this is something that we will discuss about it in the course. Another thing is, sometimes the image that we have, we don't like it with this current illumination or contrast, and we are increasing or decreasing the contrast or illumination. We make it very brighter, or we make it very much darker. Then what we do is that sometimes you have a picture, you want to make it blur. Why do the blurriness? Do you know an application of making something blur?
Face recognition, or like, what is it? Portrait mode.
Yeah, when you take a portrait photo, they do lots of blurring. Why do they do blurring?
Enhance the.
No, you don't do enhance, you enhance something else.
Yourself to look pretty.
Yeah, you enhance yourself to become pretty. I am getting old, so I use it a lot not to show the wrinkle on the face. I mean, I don't do it, but let's say. Right? If you take a picture for your passport, you cannot do it. Why? Because the wrinkles or whatever you have is kind of part of your biometric signature, so it should not be blurred by any means. We do the blurring because we get rid of some of these changes. We talk about this a lot in details, and you see that there is actually lots of more application of that one. So you do the blurring. Another reason that we do the blurring is that if you do the blurring, you can squeeze it more. Why? Because you are losing lots of details. When you lose the detail, it means that you become smaller automatically. So you make it small, you transmit it,